Hello, yeah, thank you very much for having me. I'm Kostas, the CTO of Veridise, which is a security Web3 firm. And in contrast to all of the technical talks we've seen in this event that told us how to do things or how to improve things, I'm here to tell you how not to do things, especially in the context of zero-knowledge systems. So this is a joint work with several collaborators, internal and external from Veridise, and it's going to appear in this year's Usenix. So before we dive into the main subject, let me give you a very, very informal introduction to ZK systems, just to make sure we're in the same page. So generally, ZK systems consist of two entities, a prover that wants to prove that knows a secret value, and a verifier that accepts proofs from arbitrary entities and it checks for their validity. So in general, to convince a verifier that you know the secret, you have to submit a valid proof, and the verifier will validate it independently. And generally speaking, we want every ZK system to have the two important properties. The first being that the prover doesn't have to reveal the secret necessarily. And the second one is that the verifier can always detect invalid proofs. That is, you cannot convince the verifier that you know something that you don't. So with that in place, let's see how this applies to Web3. So imagine you have a DE app that wants to commit a very complicated logic into the chain. So instead of implementing the logic directly on the chain, they will just deploy a verifier on the chain. And then a user that wants to commit something into the chain is going to run the computation off-chain, invoke the prover, generate the proof, and then post the proof on-chain. And then the verifier there will either say yes or no. So what do we gain with this? So we actually gain two things that are very important and missing inherently from blockchains. The first one being privacy, because as we said, the prover doesn't have to reveal secrets if they want to. And the second one is scalability, because for some ZK systems, it's actually way cheaper to verify the proof rather than running the whole computation. And okay, let's go and see how people typically develop ZK systems these days. So it used to be the case that when you want to implement a new ZK framework, because these things are really crypto heavy, you had to know a cryptographer, go to them, ask them to implement a new protocol, and then go ahead and deploy it. Luckily for us, that's no longer the case. There are several ZK frameworks where allow users to describe the protocol in a very higher level, of abstraction, and then this abstraction is automatically converted to a set of polynomial field equations, which then with some crypto magic, we can convert to a prover and a verifier. So the key observation here is that lead to us doing this study is that new paradigms like this tend to lead to new classes of bugs. And as a curious security company, we ask ourselves if we can actually automate detecting these bugs. And these ZK frameworks come in a lot of shapes and forms, from DSLs to frameworks implemented in languages like Rust and Go. However, to do our study, we focused on Circom, which is a DSL that at the time of the writing was kind of the most popular framework for writing circuits. And I'm going to give a very brief introduction to make sure we all know a little bit of Circom. So circuits in Circom are organized to what we call templates. And each template has an input of input signals and an input of output signals. So now the template must specify two things. First, it's going to be the logic that we're going to use to generate a proof. And the second is going to be a set of constraints that's going to be checked by the verifier. So for example, here in this very simple template, this first statement that uses the thin arrow describe a computation that's going to be used for the proof. The second statement that uses this triple equal operator is introducing a constraint that is going to be checked by the verifier. And finally, the last statement here combines these two operators. That means that, we're going to generate both something that is going to compute something to go into the proof, and also introduce a constraint for the verifier. However, we can always do that because constraints can be at most quadratic. So for cases like the above that involve some division, you have to specify computation and constraints separately. And we instantiate the blades into components. We have a special component main that specifies which part of our inputs is public, which are private, and then all of our outputs are going to be public. So in total, from this simple template, we're going to get these two different programs. One being the computation we're going to use to create our proofs, and the other one is going to be the constraints that are going to check the verifier. So one major source of bugs is that people tend to confuse which part is executing which of these statements. And specifically, we also have found that people think that, only the computation they define on the circuit is the one that is going to generate valid proofs, which is, of course, not the case because, as I said earlier, the verifier is deployed on blockchain, and then arbitrary people can post proofs. Moving forward, let's see how we can actually automate the process of finding these type of bugs that people tend to do. So to do so, first we collected known vulnerabilities from several sources, like issue trackers, blog posts, and so on and so forth. Validated that these vulnerabilities are actual vulnerabilities, and then we categorize them based on the root cause. So overall, we ended up with 4 general big categories that include non-deterministic signals. This is places where an output signal can take multiple values for the same input, which is generally bad. Cases where the constraint and the computation have discrepancies. They kind of compute different things. Unsafe component usage, where one component is using another component unsafely. And arithmetic overflows that are kind of similar to traditional, bugs in traditional programming languages. And each of these categories can contain several subclasses. So let's sample a few of these categories. First, we're going to start with non-deterministic signals. The first bug we see here is what we call under-constrained outputs, where the verifier is actually missing some constraints to block invalid proofs. So here we see a template that attempts to add 2 bits with some carry. And as you can see here, the logic for the computation is pretty straightforward. It does addition modulo 2. However, the constraints only constrain the output and the carry out to be binary, 0 or 1. So an attacker here can essentially create a proof that says, if I add 3 zeros, I can get 1, which is really bad. So the second category we're going to see is from the constraint computation discrepancy category. And here we call this type of bugs division by 0. And as you suspect, it has to do with denominators being equal to 0. So here, this template, it just tries to define division, right? So the logic for the computation is actually correct. However, as you would expect, it is not defined when b is equal to 0. However, if you deploy the verifier as is, I can satisfy this constraint if I set b to 0 by just ensuring that the reminder and the input is actually equal. These are all the classes I'm gonna focus on this talk. Let's see how we can automate detection of such bugs. And here, when I say detection, it's statically detecting things. We don't run the actual circuit to detect this type of bugs. So a key insight here is that in order to detect these bugs across all these categories, we need to be able to reason for both the constraints that are going to be deployed by and checked by the verifier and the computation that is going to generate the proofs. So the core contribution of our work is a new data structure called Circuit Dependence Graph, or CDG, that help us reason about circuits. So how this CDG works, so for every input signal, we're going to generate a node denoted with green. Then for every output signal, a new node denoted with red here. Now, for every statement that affects computation, we're going to introduce a directed edge from the source of the computation to the target of the computation. So for this statement here, we're going to generate these two edges. Then for every constraint, we're going to introduce edges between all signals that are involved in this constraint. And overall, like the final CDG for this example is going to look like this if we consider the edges for the last statement. So now, how we can automatically detect these things? The first step is, we're going to extract the CDG from our circuit, and then we're going to express each of these classes of bugs that we devised as a query over the CDG. So if the answer to our query is yes, we're going to flag the circuit as buggy. Otherwise, we're going to say it's safe. So let's see how this type of queries look like for the two classes of bugs that I mentioned earlier. So for detecting under constraint outputs, the query is essentially going to ask whether every output signal is constraint dependent to at least one input signal. And the intuition behind this query is that, like, typically you want your outputs to be a function of some of your inputs, right? So if there is no path that is a constraint path that connects your output signals with at least one input signal, then there is something problematic, right? Like you can set arbitrary inputs to your outputs no matter what you put into your inputs. So if you look at this graph, the answer to this query is clearly yes, because the outputs have only self-loop edges with constraints. So our approach is going to mark this circuit as buggy. So let's now see how we will detect a division by zero bug. So here, a simpler version of the actual query that we run is going to ask whether it's feasible for an input signal to affect the value of a denominator. And intuitively, why this is worrisome is essentially this allows users to construct malicious inputs where the denominator is zero and exploit the actual bug that we mentioned earlier. So, and then, like, this, whether it can affect the value of the denominator only if you look for statement edges, like these directed edges. So if you see this graph, it's actually the case that, like, an input signal can affect denominators. And actually, in order to answer this type of queries, we have to add some annotation to the edges, but this is kind of like simple, and we can handle that. A more complicated version of this query will also check the constraints to see if there is a constraint that disallows B to be zero, but I will skip the details for that. So generally speaking, I barely scratched the surface of, like, all the classes of bugs that our tool can detect. So we implemented detectors for 9 of the bugs that we devised as categories. And we performed, like, an extensive study over more than 200 Circom circuits that we got from 70 popular open source GitHub projects. And we manually inspected the results we got out of our tool. And overall, we found, like, 81 vulnerabilities across all the categories, including previously unknown ones. And generally speaking, the results of our analysis had, like, very low false positive rate. That means we didn't get, like, a lot of, like, false alarms. And our tool is quite effective at flagging suspicious locations. And since then, we kept, like, developing, and we have also started using it internally for our security audits. And with that, and I think I'm on time, that's all I have to say for today. Thank you so much for attending.
I'll ask a question, and forgive my naivety, because formal verification is outside my area, but like, how do we go about taxonomizing the types of bugs we seek? And so how do I think about defining, like you found, I think you said 9 you invented, but how do we go about thinking about the range of possible bugs we want to look for to get a sense of if we're catching many or few?
So yeah, I mean, like, the strategy we employed was kind of like, see what is the effect of the bug on the overall circuit. So for example, like, when you have like an output signal that is like non-deterministic, that's like really bad, right? Because imagine your circuit is like, capturing balances, right? Like, if I can prove that I have 2 balances, I will always pick the larger one. So, so to create like these categories, we also took into consideration the root cause, right? So like, for example, in the second example that I saw, the root cause is kind of like the division by 0, right? So if the things fit into like, tight patterns, like, that's what kind of like drives the categorization of like issues and bugs. Things beyond that, like, we started to talking about like, functional correctness and like, logical bugs and so on and so forth, which it's kind of like, harder to categorize because it's going to be like protocol specific. Yeah.
Can you check, like, I guess there's the programming language allows you to write the prover and verifier at the same time. Is
Yeah.
my understanding correct?
I mean, like, it allows you to like specify how you will generate like the, it allows you to specify the computation that will then you will fit, like the result of which you will feed to the prover, and then you will get the proof out of it.
So can you like do some basic checks, like the like if the forward computation step is carried out, the verification logic must like, if I do this computation then, and I use this other thing to verify, then it must verify to true, like.
So you mean to check like whether the computation and the constraints are equivalent? Is that?
Oh, it's not exactly agree, right? It's like if the computation is done like this for any inputs, then the verification must be true.
Yeah, I mean, like, that's like, you want to prove something stronger than that, right? Like, so essentially your verifier must specify necessary and sufficient conditions for your computation, right? Because it's not only the case that you want all of your all the output of your computation to be accepted by the verifier, but like you don't want like the verifier to accept like more outputs than what your computation is intended, right?
Why don't you want the verifier to check more? I mean, because like, is it not possible you want to verify, like, you can accept more than with the, like maybe the verifier just cares about checking some properties and it could be broader than what the computation can output, right? That's not.
So like typically, I mean, like, like it depends what's your definition, right? Like, if you have like a specification that says, I want to create a SDK system that like implements this protocol, right? So I can create like something that like, does the computation, and like, I know that like, for these inputs, I know the computation, the output must be, X, Y, Z. So you don't want your verifier to accept more, right? Because like, if like, my protocol says like, my balance should be 100, I don't want the verifier to say that my balance can be
That I disagree. So let's say I have a sorting algorithm, and let's say stability is not a requirement. And let's say the computation always stably sorts it, but let's say the verification only cares about it being sorted. So
okay,
in that
yeah,
case,
yeah. I mean, like in that case,
match,
right? That's a weaker notion. Of course, you can do that, yeah.
So, but I guess right now, do you have like this kind of sanity check that if the computation is performed, the verification must be true, like, or
like so this work is like purely like statically checking things, right? Like we don't do any type of verification. So we do have like work for like verifying properties, and then like some other people within Veridise, they do kind of like do work in the along the lines that you mentioned, that like every computation should be accepted by the verifier. And like, for us, we want a stronger notion that like, things outside the, what you expect from the computation should not be accepted.
So this is just like, I guess you can check for some ad hoc bugs, but
Yeah,
there's
exactly.
no-
It's kind of like pattern, like semantic pattern matching, like, this specific word. And like, it's kind of like generally like, internally in the company, it's like our first line of defense. So when, we start like inspecting like a new ZK protocol, we'll run like the static analyzer just to kind of like see if there is any, common pattern of like bugs in the code
I
base.
see.
But we do work on like, verifying properties for these circuits.
So I just also curious, like right now, a lot of blockchain companies, like they have this kind of a need to verify ZK circuits. Like how big is this market for verifying ZK circuits?
So actually we do get, I mean, like, I don't have like numbers for like, what's the total number of people that like, they do want to verify circuits. But we do get like, kind of like queries for like, different companies that like, develop ZK circuits for like, verification and stuff like that. One bigger driver of this is kind of like, ZK EVMs, where they define like very complex circuits. But like, I don't have like the total number of like projects and stuff like that off the top.